All right, so we're gonna work on a sapling problem, C13H10 No. But first, I kind of want to just highlight one important thing. So here's two molecules. How can we differentiate these two molecules? What's going to be the big thing we're actually going to be able to do that's different? So let's think about what's different between these. So the difference is the amide piece. How is it going to be different in the NMR? So the IR would be the same, right? Amide is an amide. It's going to show up pretty much the same. Maybe there's just some resonance here that's going to maybe, this resonance might make this a little bit at a lower frequency, but not much different, right? In NMR, how can we tell these apart? So this is where you need to take out your tables. There's one key peak that's going to be different. The splitting is not going to be different. The frequency is going to be different. What's going to be the key peak that we're going to look for to see the difference? So the key peak in the NMR would be these three hydrogens and these three hydrogens. So A and A prime. A is going to be a singlet. We're three hydrogens. What frequency would we expect it to be at? What ppm? We said 2.5 ppm. A prime is also going to be a singlet. We're three hydrogens. But that frequency is going to be more actually like 2.0 ppm. So that would be different. So that's the way you're going to differentiate these two possibilities. It's really looking at the frequencies from that table. Somebody might ask, well, wait a second, this NH, it should be able to do splitting with A. That'll be a doublet. Do we do splitting with NHs and OHs? No. NHs and OHs don't do splitting. All right, otherwise, everything else is pretty much going to look the same. The only thing that's going to be different between these two structures is this last little bit about where this frequency of this methyl group is at, whether it's on the nitrogen or whether that methyl group's off the carbonyl carbon over here. That's the only way you're going to be able to tell these two structures apart. All right, so I have done this problem before. I did screw up this. It's C10H13, and you can find this problem from the review from 10/24/16. It's the first problem I do on that review video that's linked on YouTube. So take a look there. So C6H16 N2. Find the degrees on saturation for me. Degrees on saturation here we have 0. Okay, what does the IR tell us? This is the IR. The IR here has a peak at 3281 centimeters. 3281. Okay, so what could be at 3281? So we can eliminate some possibilities. Somebody might have said SPCH, alkyne CH. But to have an alkyne, we'd have to have degrees on saturation, right? So it can't be that. Could be an OH or an NH. Why is it not an OH? There's no oxygen, right? We have C6H, right? So I know we get bogged down, right? C6H16 N2. Could be it's not an OH, right? Because we don't have an oxygen in the formula. So we're thinking NH. And we're not thinking NH2, right? Well, if there's an NH2, you'd have to have a doublet, right? The NH2, right? Different term. And NH2 has 2 peaks, right? If you look in your tables, the NH2 has 2 peaks. We just see 1. So that should tell us we have an NH. So how many bonds to nitrogen? Total? 3. So I know I have this piece, where I have a nitrogen bonded to a hydrogen and then bonded to 2 other things. I don't know what those 2 other things are, but I know they're not hydrogen. Right? I know it's not hydrogen. Okay? So that tells me one thing. So I got the functional group from the IR. That's the only peak I'm given. In the NMR, I'm given 1, 2, 3 peaks. 3 peaks in my HNMR. I have only 3 peaks. What does that tell you? 3 signals. How many types of hydrogens there are? But looking at this molecule, seeing C6H16 N2, that should tell you something about there must be symmetry going on, right? If you only have 3 different types of hydrogen, but you have 16 total, this molecule is symmetrical, right? You can't have 16 total hydrogens and only have 3 peaks and not be symmetrical. So literally you'd write symmetry. Good. Now let's look at those peaks. Let's look at what those peaks are. I'll write them out. Okay, so what I've done, I've just copied from sapling the 3 signals, peaks, frequencies from the NMR, and I've labeled them A, B, and C. Right? Label them A, B, and C. And then there's a hint. This is a weird hint. And it says the triplet at 1.1 conceals another broad resonance that contributes to the integral. When you hear broad, what does that make you think of? OH, but not in this case because there's no O, so it's going to be NH. So in here, so in this, is this really worth 8 hydrogens? No. The NH peak is wrapped up in here. All right, that's what this hint is saying. The hint is saying there's actually, the peaks are overlapping, right? The peaks are overlapping. That there's an NH, a broad resonance in here. How many NHs do you think there are? So if I did 1 NH, that means this peak is worth 7 hydrogens. How could you ever possibly get to have 7 hydrogens be equivalent? So the way I'm thinking about this, hydrogen comes in on carbon how many different ways? It comes on like a CH3, a CH2, or a CH. Do any of those add up to 7 to make it symmetrical? No. Right? Usually you have 2 CH3s that are exactly the same, so you have 6 hydrogens that are the same. You could have 2 CH2s that are the same, and then we'd have 4 that are the same. So in this case, how many NHs do you think there really are? Is it just 1 NH, or do you think, and they're thinking about symmetry, how many NHs do you think there are? There's 2 NHs. Now, this makes it a little tough. I probably would have given you and said, there's a broad peak with 2 hydrogens. I probably wouldn't have said it's underneath and made it a little more complicated, right? So there's 2 NHs. That's what this is telling us. So really, this isn't worth 8 hydrogens. This is worth 6. Because the other peak, the NHs, are hidden underneath there. So let's subtract that piece. We have an NH, and how many of those NHs do we have? 2 of them, right? So really it's going to be H2N2. So the H's are gone, the N's are gone. So I have H14C6. Do we see how that happened? So this said H, it said 8 H's, but it meant 6 because the NHs were hiding underneath it. And because we're thinking about symmetry, let's assume both those NHs are exactly the same. So now we have one of these. We should draw another piece. So we know we have these 2 pieces. We have an NH, and we have a NH, right? If I circle in blue, there's one piece, there's a second piece. What do we think about A? It's worth 6 hydrogens. It's a triplet. So what do we think it's going to be? What kind of carbon is going to be on there for A? It's a CH3. I believe that's correct. These are all A's. What does it have to be bonded to, or do you already know what it's bonded to? It's bonded to a CH2, right? Because CA is a triplet. If you're a triplet, how many nearest neighbors do you have? 2. Also, notice J, right? The coupling constant. What do you know about A and B? They're coupled to each other, right? So the 2 hydrogens that must be right next to A are B. So these are H, B. And we don't know what's over here. But here's where it gets a little, this is where the symmetry comes in. Do we have just one of these kind of CH2, CH3 pieces? We have 2 of them. We have this one and another one, just like it. Right? So I can shrink this up a little bit. So we'd have another piece that's just like that other one. Right, because this was 6 hydrogens, so we have to have 1, 2, 3, 4, 5, 6. These A's are all the same. and 4 of the B is 1, 2, 1, 2, so it's 4. And the molecules have to be symmetrical, right? So these are going to have to be in probably opposite ends of the molecule. So now we have 4 pieces, right? Do we see our 4 pieces? So we got our 2 NHs and our 2 ethyl, right? Ethyl, CH2, CH3, CH2, CH3 pieces. So what do we have left to have now? So we've crossed off, so let's see what we've crossed off. We've crossed off this, crossed off this. Now let's look at C. C is worth 4 H's in their singlets. So what kind of piece is that going to look like, do you think? So it's going to be a carbon. How many hydrogens on that carbon? 2. And what do we need to say about what on either side of this carbon? So there's singlets, that means what? No neighbors, right? So we need to write here, no neighbors. Right, because they're singlets. We must have 2 of them, right? Right, the squiggly lines mean I don't know what's bonded there, but I do know it can't be a CH, right? Because otherwise these would have a neighbor, right? They're singlets. Everybody see that? So we can say, okay, we've accounted for that. Now the last thing, what's the last thing you do now? So you found 4 pieces, right? You found a bunch of pieces. We got a couple CHs with no neighbors, got a couple CH2, CH3s. We got a couple NHs. Now we got to decide where to put this all together. Now you go back and look at the frequencies. The last thing you do is go back and look at the frequencies and look at your table. So now I want you to go back and say, okay, 2.83 and 2.66 and 1.1. Now you got to decide, right, where things go. Who's going to be bonded to the nitrogen? Right? Who's going to be next to it? So think of the ways you can put these pieces together. So a couple things. HB is at 2.66. If you look on your table, that should tell you HB is a little deshielded because it must be bonded to that nitrogen. So this carbon is bonded to that nitrogen, and this carbon is bonded to the other one, right? But think about the molecule is symmetrical, right? We're kind of building it from 2 different directions. So one side is going to look like this, right? And these are H, these are B, and these would be A. What about C? Where does C have to be bonded to? If you look at its frequency, what does C must be bonded to? Is C going to be bonded to that nitrogen? Yeah, it's going to have to be. But then what's on the other side? So that's great. That's C, right? What do we have left over here? Just essentially, it can't be the other nitrogen, because if there was the other nitrogen, this would be much more deshielded, right? We need actually this piece again. Right? Think about it. This is like the other half. This is like one half of the molecule. The other half is mirroring it, right? Remember this symmetry. And remember, can you couple to yourself? No. Let's just look at you can't couple to yourself. So both of these, there's 4 HCs in the middle. But you can't couple to yourself, remember? They're all singlets. And then on the other side, yep, that's the tricky one. There's your HB. And then all of these are A. So I'll draw a cleaner picture here. The final thing looks like. So the final thing should look like this. There's your final structure. So these are the C's, the 4 HCs, the 2 NHs, HB, HB, HA, HA. So this is really if you go beyond that. Yeah, so it's really hard, right? So this is weird because usually the benzene ring ones are easier to see, right? Because we think of the benzene ring as kind of flat, right? and you know it can't rotate. Now this one though, just literally think about dividing this molecule. If I just went like this and cut this down the middle, is it any different on either side? If you go from any point, if you go from this carbon and say, what is this carbon bonded to? It's bonded to 2 hydrogens, a carbon, and a nitrogen. On the other side, this carbon is bonded to 2 hydrogens, a nitrogen, and a carbon. That's a methyl, that's a methyl. Same, so everything's exactly the same, right? But it's just weird to see in like this. So these 4 hydrogens are all the same. Right, C10H1002, we calculated the DU to be 6. If we see a DU of above 4, what do we think? Benzene ring, right? Benzene ring, ding, ding, ding. Ding, 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 benzene ring, right? Because a benzene ring covers 4 degrees of unsaturation, right? A ring and 3 pi bonds, that's automatically 4. So when we see something like this, we should be thinking benzene ring, right? Benzene ring. What did the IR tell us? The IR said 1681, and they said no OH. Okay. 1681. What is that? So there's no hydroxyl. What's around the 1681? And don't forget our degrees of unsaturation we're gonna have to satisfy. Yep, I would be thinking, 1681 is right in that C double bond O region. Do I know exactly what type of carbonyl? Nope. I have no idea. But I know there's probably a C double bond O in this molecule somewhere. Okay, so that's what 1681 told me. Now let's look at the NMR. The NMR only has, so this is the IR. This is the kind of thing I would expect you to write out exactly, just like this, on your exam. Now the NMR has only 2 signals. What does that tell you here? 2 signals, C10H1002. Only 2 peaks. Symmetry again, right? These symmetry molecules. Symmetrical molecules. Symmetry. Very symmetrical. We see a peak at 2.82 and another peak at 8.13. This one is worth 6 H's and it's a singlet. This is worth 4 H's and it's a singlet. So a couple things to look at here. Let's look at 8.13. What region in the NMR is that? Benzene ring, the aromatic region, right? And it's worth 4 hydrogens. So what does that tell us? What kind of benzene ring do we have? It's probably it's for sure symmetrical, but then also how many substituents are off the benzene ring besides hydrogen? 2. So it's a symmetrical benzene ring. So let's subtract that piece out. This is already telling us this. Like, we have a symmetrical benzene ring, and I did 1, 4. I did the 1, 2, 3, 4, right? Because that's the best way to get things symmetrical in a benzene ring. To be disubstituted, remember that? This kind of substitution pattern. So let's subtract out that piece. C6, how many hydrogens is this worth? This piece down here? How many hydrogens on this? How many? 4. Good. H4, so we'll take that piece out. So we got C4H6O2. And if we labeled these, if this was A and this was B, these are all HBs, right? They have to be all the same. So if all of these HBs are going to be the same, what does that tell you about whatever's bonded here? Has to be the same too, right? So these HBs, right, for these 2 and these 2 to all be the same, whatever's on either side of this benzene ring also has to be exactly the same, right? Has to be exactly the same. So we've covered this one. What about 2.82, 6 hydrogens in a singlet? What is that? What region does that tell you? 2.82 and a singlet, 6 hydrogens. Can carbon have 6 hydrogens bonded to it? So is it really going to be 6 hydrogens, or is it going to be 2? It's going to be 2 CH3s, right? It's really 2 CH3s. 2.82. What do you think it's bonded to? What do you think is near? 2.82. Ooh, be careful. Like an OA, so don't forget your little table of known things. 2.82. We talked about oxygen. That'd be like 3.5. 3.5. 2.82 is not 3.5. It's not near a nitrogen. What's the other kind of region? That's halogen would be like 4.5. Allylic, the allylic region. It's a little high. It's a little high, right? The allylic region usually stops at 2.5. But, right, we know it. I mean, I'd rather have it be a little high than too low, right? If you're next to an oxygen, you're gonna be at 3.5. You're gonna be a little higher. So we should be thinking, right? CH3s. Maybe we don't know. Maybe it's too hard to guess. But we know we have this, right? We have two CH3s, and we label these like these are the A's. So let's subtract those pieces out. Maybe we're not sure yet. Maybe they are next to the oxygen. I don't know. Let's just see what falls out. So how many carbons is that worth, those two pieces? C2H6. So we end up with C2O2 left, right? So what are those going to be? And don't forget, that's the first thing we talked about, the IR. We thought we had carbonyls. Well, what do you think these two are? It's two carbonyls. So those two pieces would be this, and then I'll draw, we'd have another one, right? So that would take down the C2O2. Do we have anything left? So what are our final pieces? We have this one. We have the benzene ring. We have two carbonyls. We have two CH3s. So I said two carbonyls because we end up with C2O2. And I know the molecule is super symmetrical, right? So I couldn't just have one carbonyl, right? When you see symmetry, essentially you're going to have either two of everything almost, right? Because there's going to be mirror planes of the molecule. So I knew there was a carbonyl. It ends up being C2O2, which makes me think two carbonyls, so I drew two carbonyls. So you end up having 1, 2, 3, 4, 5 pieces. How are you going to put it all together? Right, so finally putting this together. Technically, there's only one way to do this, right? Because the carbonyls are the only places that have two spots on it. If I try to put the benzene ring with these methyls, I wouldn't have a place to put the carbonyls. Right, don't forget, how many bonds does carbon have? 4. There'll be no pluses or minuses in these problems. So carbon only has 4 bonds, so the benzene ring attaches to one of the carbonyls, and the methyl is on the other side, and then it's symmetrical here. So all 4 of these hydrogens are the same. Right, these are all HB. And in the red, all these CH3s are all HA. Now let's make sure things match up. Would A be a singlet? Yes. Were 6 hydrogens? Would B be a singlet? Yes. You can't couple to yourself. Do the frequencies make sense? 8.3, that's in the aromatic region. That makes sense. 2.82 maybe seems a little high, but is it outlandish that it's that high? No. Maybe it's getting de-shielded because of all the pi bonds. So that maybe is why it's a little farther downfield. It's getting de-shielded. So there's your answer. So taking a look at understanding carbonyl differences in their frequencies. So in the middle here we have a ketone at 1710. To the left we have an ester. To the right we have an amide. When we're talking about what bond we're talking about the C double bond O. We're talking about that C double bond O stretch. So we know, what do we know? We know when this bond is shorter, does it stretch at a higher or lower frequency? When this bond is shorter, it's going to stretch at a higher frequency, right? Because it's going to, right, shorter bond, higher frequency. So that must mean that in the ester, this C double bond O is becoming a little shorter. On the opposite end of the spectrum, this is a lower frequency. That tells us that this C double bond O, right, must be becoming a little bit longer, right? It's a lower frequency. That must not be that short of a bond. It's a little bit of a longer bond. Now, why is that? So let's think about it. What could be going on in these two cases? First of all, we have a nitrogen versus an oxygen. What do you guys know about nitrogen versus oxygen? What's the major difference between them? Electronegativity. Which one's more electronegative? Oxygen. So I would presume maybe that this oxygen is pulling away electron density. And what's that going to do? That's going to shrink up, right? As it pulls away electrons, that's going to shrink up this bond and make it shorter. Make it go to a higher frequency. Now, can an ester still do resonance? Yeah. All this is saying is that resonance structure that likely to happen? No, it's not the most important thing here. The most important thing here with esters is induction, right? Pulling away electron density. It can still do resonance, but it's not the most important factor here. It's about induction. Now on the other side of the coin, look at that amide. Now it's a nitrogen. A nitrogen is electronegative, and certainly this is, right, certainly this nitrogen is pulling away electrons, but that's an amide bond. And nitrogens are much more likely to do, right, to donate electrons. So it's more likely to do this resonance structure. Now what's that resonance structure look like? It looks like this. What happened to our acetyl bond O? Now it has some single bond character. Single bonds, right? That's going to make it a little bit of a longer bond. So if it has some single bond character, that's going to lengthen this out. And that's going to make it stretch at a lower frequency. So in this case, resonance is more important. In this case, induction is more important. It's all based on, right, the electronegativity of oxygen versus nitrogen. Crucial to life. This is why we're standing here. This is why peptides and proteins. If this wasn't the case, if we were all based on esters, we'd be hydrolyzing. It'd be very bad. So this is one of those things. Super important.